Good afternoon. You should be in ceramic processing principles. At least that's where I am. So if you're not, this is a great time to go. I'm Bill Carty. If you haven't met me, this is a syllabus more or less. Okay, and this is a calendar. I have some travel coming up in this semester. Unavoidable. What does that mean to you? That means that you kind of get the day off, probably. You have one of those. And we'll talk about that as this progresses. There are two homeworks that I'm assigning you now, okay? And we will talk about those also. Technically, this class was scheduled off the grid. You know what that means? There's a grid, and somehow this class got scheduled off the grid as a Monday, Wednesday, Friday class. Technically, it's supposed to be Monday, Wednesday, Thursday. You follow me? If you follow the grid. I don't know why you get scheduled that way. If you have a conflict on Friday's meeting because that's actually a different grid slot, let me know. All of you should have the next hour free on Thursday. Correct? Yes. Okay, because the grid spot is blocked. All right. This is a book for the class. All right. So it's worthwhile to get. Jim Reed was a professor here. He was here when I got here, and he retired a long time ago. I like this book for some things and not for others. The stuff that I don't like, I'll give you handouts for. We'll work through it that way. Okay. I think the colloidal behavior stuff is a little weak, and so I encourage you to read the stuff I give you instead. All right? And we can talk about all that, of course. How many of you had 203? How many of you have not had 203? Okay, so how many of you are material science students? Anybody bio? All right. Any mechanicals? All right. So, I'm going to keep my pithy comments to myself. You can already figure out what it looks like. We are piloting a series of laboratory exercises within ceramic engineering, and they are set up to be A block, B block type of labs. 1 credit hour labs. Meet once a week, and then you have a lab meeting once a week. If you've not had 203, I would encourage you to take the one that meets this afternoon in the hour after this, which is powder characterization. And if you are a material science student or bio or glass, anybody glass? Good for you. Or mechanical. It's basically a 1/2 semester class with a lab on powder characterization. Okay. The reason that we're doing this is we're trying to develop a whole series of short, focused lab experiences that get you more hands-on and more exposure to equipment, okay, measurements, etc. And this lab will do that. Our first meeting time is this afternoon. 3 of you, 1 person in here is in that lab. Who's that? You. Perfect. Okay. So you can attend today without registering for it, see what it looks like, and then register after that if you so desire. The second lab that's offered this semester, which is in the B block, is thermal analysis. Okay, which it sounds as exciting as it is. It is a rockin' cool lab exercise. We do differential thermoanalysis, thermogravimetric analysis, heat transfer, thermal expansion, thermocouple behavior, etc. Okay. Also, a 1 credit lab meets at the same time. It will be a lecture in the lab, okay, throughout half the semester. That one you don't have to register for a while. okay? But I encourage you to do that also. Other labs that will come online as the next couple of years evolves, include mechanical properties, electrical property measurements of materials, et cetera, et cetera. We're going to take 203, if you took 203, and we're going to break 203 into 3 labs. Okay? You can debate whether you think that's a good idea, and you can tell me what you think. Okay? But one lab is powder characterization, the second lab will be photo processing and rheology, the third lab will be ceramic forming processes. And what that lets us do is you actually get more lab exposure to those topics than we can do within 203 in the time frame allotted. And then the lectures, actually we reduce the lectures by a little bit. So instead of 2 lectures per week plus a lab for a full semester, you have 1 lecture in the lab for half a semester. I think it's going to work out very well. As ceramic engineering students, you would be required to take that. The benefit for students that are not ceramic engineering students is that they then get to take these lab exercises, so they don't have to take all of them in order to fulfill their requirements. So 203 will go away. Make sense? Okay. I encourage you to take powder characterization. If you already took 203, I'm willing to let you take it again. What does that tell you? That tells you that we may not cover exactly the same stuff this time as we did last time. And the benefit, as I see it for these labs, is that it gives me more time, gives you more time to learn the material, so we can do things in the lab that we didn't have time to do during 203, because I have 50% more lab time. Right? That works out really well. So that lab meets, the lecture is this afternoon, right after this class, 2:20. I don't know what room it's in. Is it in this room? 244. 3? Anyway, I'll find it. Maybe. All right. So this is the syllabus. This is the text. There's a bunch of other really good texts available. Not that many for ceramic processing, but in general. Rohaman's text, Ceramic Processing and Sintering, 2nd edition, you will be required to purchase when you take sintering. So if you feel like getting it now, it's excellent. And I've known Rohaman for years. He just retired from the University of Missouri Science and Technology. And he did a great job in this text because he's an expert in sintering. He's really good at sintering. But he wasn't an expert in processing, and he did all of his homework in the literature. So what you have is a really great summary of the literature with regards to processing. So I think very highly of this text. But this class works better with Reed's book as an introduction to processing. Okay. The next is Barnes, Hutt, and Walter's Introduction to Rheology. If you find that in a used bookstore, buy it. If you find 2 copies, buy 1 for me. So buy 1 copy, you don't want it, give it to me. Very difficult to find, very, very expensive, exceptionally well done. The problem is I wanted to use it as a text, so it was perfect. It's just too expensive, like $250 for a copy. My copy has inconveniently disappeared. I wanted 3 copies, so that's what happens. It'll come back eventually, maybe. Hunter's book, Introduction to Modern Colloid Science. Great, pretty advanced though. Mineral processing technology, there's a lot of those books around. They're good. We talk about mineral processing because it's a precursor for how we get particles in ceramics. Kingery, Introduction to Ceramics. You should have it. If you don't, you should go get it. You can find it used, and it's cheaper unless the people who are selling it know what it's worth. You almost always find it much cheaper than it is for new on the shelf. Hasn't changed since 1975. Not likely to change since Kingery died a long time ago. Science and Wires 1 and 2, and after you find those, that's good, just pick them up. And ceramic engineering science proceedings are good, but they're no longer being published. This is the way I break down the grading, sort of. I'm not real good on homework. In fact, I don't grade it. I'm not planning to grade it. I have a grader, but still not probably going to grade it. Okay? I will grade the exams, though. So here's what I will try to do, and I say try because schedule permitting. I'm going to give you a homework assignment, and then I'll publish or post to Canvas the answers to the homework assignment somewhere around the date that it's due. So why don't I grade homework? Because it's a waste of your time and it's a waste of my time. How's that? I look at the problem, you answer the problem correctly, I mark it wrong. That doesn't help you at all. Fair enough? Okay, it'd be much better for you to do the homework in advance by the due date. If the answers are set up then and you can read them, you can see, how I approach the problem or how I would like you to approach the problem. Much better way of doing it than having me grade the homework. Okay, it says that 30% of your midterm grade is homework. That's probably not going to happen. All right, so your midterm grade is going to be pretty much dictated by your first exam. What does that mean? That means if you do poorly on the first exam, that really has nothing to do with your final grade. Fair enough? The same could be said from the other way around. If you do great on the first exam, that doesn't make any difference either. I mean, it'll help you, right? But it's not going to indicate what your final exam or final score will be. Fair enough? Great. There is an interesting correlation. How you do in the first exam is usually how you do in the second one and the final. Remarkably consistent in that manner. I propose that you would buck that trend in a positive way. Don't do well on the first exam and ignore the second. Fair enough? Okay. So, I have a get out of jail free card at the bottom. Grading policy and distribution can be changed as I see it fit. Right? What does that mean? It means exactly what it says. Here's the thing. Up here, office hours by appointment only. All right? I don't have office hours. I don't keep office hours. This doesn't mean I'm not in my office. I'm in my office a lot. I just don't have regular hours. Why? Because I could put on a piece of paper that I'm going to be there from 9 to 10 every morning. I usually get here at 8. That doesn't mean I'm going to be there in my office from 9 to 10. And this is going to come as a shock, a bit unfortunate, a bit rude, and I'll sit around waiting for you to darken my doorway and ask me a problem. Fair enough? If you want to meet with me, email Krishna. That's her email address, amin@alfred.edu. You can email me. What will I do? I will send it to Krishna if I read it. Okay? And then that just delays the process. Krishna is awesome. She controls my calendar. Okay? If you set up an appointment for me and something happens and I get delayed or I'm not in or a meeting I'm in goes long or lunch takes longer than it should, which is not uncommon, then she will automatically contact you and change the appointment. It's so much better than dealing with me directly. Okay? And then if I'm not there, she will remind me. This is much better than office hours. Fair enough? Okay. Move the schedule. The schedule is more or less designed to follow this path. Okay? There are some things in here that are light shaded boxes that don't show up very well on the projection. The far right hand column is what we're dealing with. Okay? I will let you know chapters and read that you should review. I will post handouts to Canvas rather than printing them out for you. There are some references in the literature that we use every year because they're so good. Southern oxide Blier's polyelectrolyte absorption paper is a landmark paper, and we use it. Okay, I won't typically hand those out. I'll post them to Canvas for you. You can print them from Canvas. Okay. This week here is MS&T, and I have the little stars in here to tell you I'm not going to be here. I don't know how I came up with that idea. It's not very good. This week I'm gone the whole week, and right now I'm leaving. I think Wednesday afternoon or Thursday morning. I think it's Wednesday afternoon because other things I have to do in Portland, Oregon, and it's a long way, and then I have meetings in Seattle after that. So I won't be back that whole week. We have off. So what am I going to do? No, that's not the question that you want to answer. The question is, what are you going to do? That's when you have an exam. No reason for me to be here during the exam. Fair enough? Okay. So we try to schedule it that way. I'm also out the 12th and 13th of September, and very likely we'll miss class on the 11th of September. If it's a topic that my grad students can handle easily, then they will teach for me. Okay, that happens. It works really well. And if not, we'll try to make up those times at another time. Good. The last one that I know I'm going to be out on, or right now, still kind of pretty sure I'm going to be out, is Thanksgiving. The whole week of Thanksgiving, I'll be in China, so we'll be out. Okay, good. It just disrupts you in terms of you don't have to come to class. Currently, I thought that here in China, in the week of Thanksgiving, whatever comes to mind, looks like it's going to be Chinese, so I guess we're going to go from that one. All right. So, you have 2 homework assignments I just passed out. Let's talk about that briefly, okay? From experience, having you do a research paper or a project is really beneficial, and it lets you get a little more involved in the subject than you would get out of the lecture. These are group assignments. Almost all of the homeworks are intended to be group assignments, whether they state that at the top or not, okay? Besides, you're not turning the homework in, so if you do it by yourself, that's fine. But I really encourage you to work in a group. Now, for this part of it, for the project, group of 3 is ideal. At the moment, there are 29 students in here, and I can do that math. That doesn't work very well, okay? But a group is at least 2. There are no groups of 1, fair enough? And groups of 4 usually means one person doesn't do anything, so we prefer to have groups of 3. If you get to the point where you can't figure out how to cut somebody off and have only 3, we can discuss it. Fair enough? Okay? So, form your groups. You need to tell me who your groups are by Friday. How do you do that? Email me with your group names. Copy your group members on that email. Right? That's important. What's the subject line say? Subject line has to say this. And then I don't care what says after that. Okay? Please put that in the subject line. Why? Because I can then find it later. Right? So I can sort by subject and I can find all the emails that came from this class. Because I get about 100 emails a day. I don't know how many emails a day you get. But a lot of them are nonsense, but some of them I have to deal with. But this lets me go back and find it. Good? Please put that in the subject line. If you email me about your group or your project, please copy the other people in your group. That allows me to reply to all. Otherwise, I got to figure out who your group members are and go find their email addresses and then email all of you together. I'd rather have it that way. Make sense? Please do that. That's the best way. You can read through this. It's pretty straightforward. You have to select your group and your topic, ideally by Friday. All right? Why am I doing that? Well, I have 2 things, right? You have, by Friday, you have to identify your groups. By the 20th, which is, that's the wrong date. No, that's the right date. On Friday, a couple weeks from now, 4 weeks from now, you need to have an abstract. The reason that I do that is that we're all expert at procrastination. I would even hazard that you were better at it than I am, and that is significant. Okay? So you will wait till the last possible minute to think about your project title and to think about what you're actually going to talk about. Is that a fair assessment? So I give you a deadline, and you have to meet the deadline, or else then you have to do something else. So let's not do anything else. Get your groups figured out this week. Let me know at the end of the week what it looks like. Let me know your topic. And then what we can do is in the next week, the week after this, we can set up an appointment with Krishna, and ideally the 4 of us, myself and the 3 of you, will sit down and discuss your topic and which direction you're going to go. I have 2 tasks, right? One is to make sure that your topic is germane, and the second is usually to rein you in from doing a topic that you can't possibly complete in a 3-year PhD dissertation. Fair enough? Okay, so I want to meet with you. I want you to think about what it's going to be. You're going to have a topic picked out ideally by Friday, right, that you submit, and then we can talk about it. If 3 groups or 2 groups come up with the same topic, then we can iterate around that and figure out who gets to do what. Fair enough? So you need to find 2 other people in the class that you can work with and set up a group and let me know. Good? That's your first homework assignment. The second homework assignment is this one, which we will address over the next week or so. Now, at the top of this, okay, due date September 6th. That gives you some idea, right? And then it says opportunity for in-class discussions is going to be, of course, Wednesday as possible, but Friday and the following Monday. All right? Well, also the following Wednesday. The opportunity is I will answer any question about the homework. Anything. I'll walk you through how to do the problem. Although it's better if you've already attempted to do that instead of saying, can you show us how to do number 3? Right? Fair enough? So do that. If you run into a block and you can't figure it out, right, you can either email me and set up an appointment, or you can bring it up in class. My preference is that you bring it up in class because it's very unlikely that you are that unique that you can come up with a question that no one else in the class has. Okay? So everybody here is the same answer from the same question, right? And then everybody is now on the same page. That works much better. I'm happy to meet with you individually, okay, or as a group ideally, okay? But I prefer that you ask the question so that the class hears the answer and the question. If you are shy and you don't want to ask the question in class, I will have Krishna set up a Canvas discussion forum thing, whatever it's called, okay, where you can post questions about the homework to Canvas. Fair enough? Your responsibility does not end at that point. What else do you have to do? You then have to email me to tell me that you posted a question to Canvas. This is going to come as a shock, but much like I deal with Facebook, not on Facebook, that's how I deal with it. I don't stalk it. I don't sit there and wait and every night pull up Canvas to see if someone posted a question. Okay? If you will have overestimated my level of interest if you think that's happening. Okay? So you have to let me know if you post a question to Canvas. If you post a question to Canvas, I will answer it on Canvas, ideally. Okay? But if I don't, then I'll address it in here. Fair enough? That's the best way to approach the problem. So if you don't want to talk up in class or speak up in class, I'm fine with that. But you have to then, if you want to get the question out there, you need to put it on Canvas, but you have to let me know. Okay? If you don't let me know, then I'm not going to know that it's there. Good? Okay. So what we are dealing with, any questions? That's pretty much all the mechanics stuff we have to deal with. Okay? I try to teach this class as if you haven't had 203. Okay? It's an attempt. It's not a very good attempt, okay, because 203 is really valuable because you get to see how these things work. We have a debate among the faculty. It's sort of a pointless debate. But there's a small group of faculty that think that students learn better from theory first and then hands-on second, which is utter nonsense. There's like probably 3% of the population that learns that way. Everybody else learns the other way around. Do and then figure out the fundamentals, if you will. And that's sort of the problem of this class is that if you've had 203, you've already seen the behavior. And so one of the oppositions to creating all these new labs for the program is that, well, they're going to see the lab before the theory, which the answer should be perfect. But instead the answer is, oh, I don't think that's a good idea. So I believe that hands-on is really a great way to do this. To that end, if you've not had 203, if you're not a ceramic engineering student, you can sign up for an independent study and we will walk you through the lab sequence. We'll let you actually go in the lab and do that. We did it last semester. I think it worked very well. Okay, you do not have to do it, but I have a grad student who will teach that. You meet once a week. You don't have a lecture attached with it. It's just you get to go in the lab and do the exercises and see how things work. If you wish to do that, we can set that up. Okay, it's not formal, it's informal, it's an independent study. Okay, but it's designed to deal with the colloidal behavior and the ceramic forming processes aspect of 203. Okay, so that is an option that's open to you. You do not have to do it, but it's an option. The other is this 1-credit powder characterization lab, which will be really good. Okay, so that's the way we approach the problem. All right. So here's where we are. Why do we do ceramic processing? Okay, so basically it's this. Ceramics have extremely high melting point. Okay, if you want to compare that, my best example is aluminum metal, right? Aluminum metal melts at about 600 degrees C. Approximately, it's approximate, close enough. Aluminum oxide, this is why my best example, melts at 2050 degrees C, and that's actually a measured value, okay? It's extremely high melting point. Ceramics, by and large, metals, everybody melts them, pours them in an ingot, right? Because of ductile behavior, they'll roll them into shapes, hot rolling, cold rolling, whatever, and you get sheet steel, you get wire, you get I-beams, whatever, right? We can't do that with ceramics. We don't start with raw material melted, form it into something. There are only two industries that do that. In the ceramic world, glass is one, of course, which is sort of pushing the boundaries. We still consider them ceramic, but we're talking about glass forming processes, very viscous fluid. The other is fused cast refractories. If you take my refractories course in the spring, we'll go over to Falconer, New York, to the monofrax plant, where they arc melt alumina, zirconia, and a bunch of other things. Screaming hot, awesome. They cast these blocks, and then they knock the molds off. They're still glowing red, and they put them in, let them anneal for 3 weeks to cool down. How cool is that? Or hot, space can be, right? So those are fused cast refractories. Benefit, great for refractory applications. Impractical for everybody else. So we don't do that. We start with powders. Okay, we have to deal with the powders, and we have to learn how to control those powders. And then what we get in that process is shrinkage. Okay, so for example, this is a pretty slick process. These guys in Pennsylvania are making these are for called vacuum disconnects or whatever. So the high voltage things, they put them inside. This is the green piece. This is when it's sintered. That's the difference. Okay, this is real, right? And this is this part sintered. Okay. Now I would pass this around, but I'm down to my last few of these because it usually doesn't make it around the room. Someone will decide, it's pretty strong, and then find out that it isn't. Okay, so I'm not going to pass this around. You get to look at it. I'll pass this around. You can break this one. I'll be impressed. Okay, that's the sintering problem, right? The green state, you don't have sufficient green strength. We have it to handle. We can handle it. We can deal with it, but it's not ready to use. We have to do the sintering step, and then you're looking at 20% shrinkage in that process. That would be more or less perfect, right? Now you have a problem. Okay, if it shrinks uniformly, no problem. If it doesn't shrink uniformly, you get two cases. One is that it can warp, not stay as a nice cylinder. This is actually pretty close to being perfect. There is a little bit, if you measured it, you find out it has a little bit of an hourglass shape to it, but it is almost perfectly round. Not exactly, but pretty close. The other thing that happens is, what did I say? Shrinkage is one. Oh, I know, warping and then cracking. Right? You have those two things. Right? Warping is when you have an area of high density versus low density. High density area will warp. We'll talk about that specifically. Cracking is when it wants to shrink more in one place than another. It reaches a state limit and it shrinks and cracks. Okay? So I'm handing you the one that is unbreakable for the most part. It can be broken. You have to work at it, all right? What do you think? So, all right. So the problem is, right, we have to deal with that. And a lot of the stuff that we're doing is then how do we control powders and how they interact. That's where colloidal processing comes in. We start with fine particles. And what's been happening over the last 30 years, 40 years, 50 years, those particles are getting smaller and smaller. And as those particles get smaller and smaller, attractive forces, Van der Waals attraction forces, start to dominate that material over gravity. Now we have to figure out how to control that attraction between the particles so that we can get uniform particle packing. So when we get to the sintering stage, everything sinters in a uniform manner. That's really, in a nutshell, what ceramic processing is about. And then we confuse the issue by talking about forming techniques, which we now own better than we used to. So this colloidal processing thing is key. So we're going to spend time talking about colloidal processing. How do you control the interactions between particles, and how do you then manipulate that interaction to get the performance and the behavior that you want out of the system? Processing defects limit yields. Yields is how many pieces you put in the box compared to how many you made. Okay. Properties, performance of ceramic materials and components. That's where we're at. You want to think that the sintering process, taking that material, putting it in a furnace and heating it up, that's the key step. It is not the key step. This is the key step. All the things you do here in processing show up when you put them in the furnace. It's not the problem of the furnace. It is rarely the problem of the furnace. It is almost always your process technology and your performance in processing that dictates how that material behaves. That idea is hidden at the moment. And there's only a few groups, frankly, in the world that recognize that that processing step is the most critical. Everybody else is dealing with drying stresses and sintering behavior, et cetera, et cetera. Okay, this is the key. Oh, that brings up a great point. What about 3D printing? Anybody worked in 3D printing? Anybody interested in 3D printing? You know what I'm talking about? Additive manufacturing. It's a shiny object in the room. You're not used to this, are you? It's going to continue. Apparently I didn't write the slide. We're talking about traditional processing versus 3D printing. 3D printing is a mature technology for plastic. Good. It's pretty close on metals. A lot of materials are 3D printed. It's nowhere close to being ready for ceramics, in spite of what you read in the media, in the American Ceramic Society, in the bulletin. Okay, there's a huge amount of nonsense published about 3D printing. All right, all of the problems that we face in traditional ceramic processing, and I'm not saying traditional as in clay-based systems. Everything that we face in our conventional ceramic processing is present in 3D printing. We just choose to ignore it. Okay. And so we have a 3D printing lab. We have two what are called binder jetting systems, where you put down a layer of powder, and then you print the binder where you want the material to remain, right? We have two of those. They're interesting. And then we have one which is photolithography. That's interesting. And then one of our alums, as well as board trustee member, and the guy who wrote Cesaron Oxide and Blyer, Cesaron, developed the third technique called robocasting, okay, which is essentially extrusion technique, and you basically direct where that extruded cross-section will go. We use that technology now to print houses out of cement, for example, okay, which is kind of cool. Right? What's the benefit? No sintering. Good? You don't have to sinter cement. The problem here is that what you may think about 3D printing is probably false. How does that flow when unsintered? You want to do the photolithography route. If you change your composition, go back to the company, and 6 months later they'll give you a slurry that will work for photolithography. No, not interested in that. And then if you do the robocasting, you have some problems of how you control flow. We have good ideas about that. But the bottom line is that if you get a powder that will flow in 3D printing, it will not sinter, period. You can engineer a powder to flow that jacks up the surface area for potentially able to sinter. Still doesn't sinter well. It's pretty cool. We think we figured out a way to sinter those systems, but that's like 3 to 5 years from now. And it's 3 to 5 years from now because somebody's got to give us a boatload of money, and I have a couple PhD students work on the problem, and we'll stop. But it's not ready now. And so you read about all the hype about 3D printing. All of it comes back to processing. Okay, and it's simply not there. And all the problems we see in processing are not going to go away because you put a computer in the front end of it. I will eventually probably talk about 3D printing in here. I think it's much better to understand the process part of it. Questions? I get all wound up about 3D printing. Now, a friend of mine, brilliant guy, says all these smart people check their brains at the door when it comes to 3D printing. Right? And then there's a group, I just saw this, still working on it, where they're laser welding ceramics. There's a problem there too, right? And direct printing, like where you lay down ceramics and sinter it at the same time, and then it cracks and you're surprised because you've ignored all the heat transfer, thermal expansion problems, and the fact that you were working with a brittle material that doesn't do well in absorbing strain, dissipating strain energy. I can go on and try not to. All right. We do a lot of stuff with alumina in our processing, and the reason that we do that is because, one, we've spent a lot of time processing alumina, and two, the problems that are associated with processing alumina are pretty much as bad or the worst problem you can run into in processing. So it's perfect for us, okay? Very high attraction forces between the particles. What's cool about alumina is I can get boulder size alumina down to nanoscale alumina, and it's all roughly the same chemistry. That means that we can play around with particle size, we can play around with the effects of size, we can look at the sintering problems, we can play around with colloidal interactions. Alumina's perfect. Okay? The background, you have a 1 micron size bar at the bottom. That's this background here. You know, these are basically commercially available powders. And we can purchase, which we prefer not to do, or call up and have donated powders of any size, and that's great for us because it lets us work with this material easily. We work with it in the 203 lab. We work with it in my lab all the time. We use alumina as an example of how other things will behave, and that example is not bad. Okay? These are hip replacement balls. This is zirconia. This one's great because it has a defect in it. You can actually feel it. Okay, and this one doesn't appear to have a defect. The zirconia thing is great. Okay, processing problems are pretty much exactly the same as they are for alumina in terms of getting it into this shape. Zirconia, though, because of its nature, allows you to polish to that surface finish. It's hard to do that with alumina for reasons I don't really understand. Okay, because I think you can do it with alumina. But the reason that they like zirconia is because if you put it in water, the surface pH is neutral. Put aluminum in water, surface pH around 8.5. Put silica in water, the surface pH is like vinegar, around pH 2 or 3. Right? So you put silica in the body goes, whoa. You know, who did that? Have you ever had a cut on your finger and then cut into an orange? That's citric acid rather than acetic. This is why we like oranges. Okay, but you know, it burns. Body does the same thing. You put glass in the body goes, this is not happening. And all it does then, from that point on, is figure out how to dissolve that glass and get it out of there. Great for time release chemistry and stuff like that, right? For things that are going to go away. This doesn't do that. The reason this doesn't do that is because the body doesn't see it as a foreign object, because its surface chemistry looks like everything else in the body and is neutral. So zirconia works for that reason. Okay, I'll pass these around because they're cool. All right, they start with a powder also. I'll give you the defective one. The other one will eventually make its way back here. All right. So there's a small company down the street who makes those. They start with the powder. They make a preformed isostatic press it, and then they sinter it. And they run into problems in processing also. But same problem that we have with aluminum. I have this little device here. This piece actually was HP made this about 10 years ago. And it is a printer part, actually. It was for a high-speed inkjet printer. That's not focused on. So, 82 critical dimensions made by injection molding. And at the time, they liked the ceramic better than anything else because inkjet printers, the head gets heated, and they could exactly predict where the droplet was going to go by working with the ceramic versus a polymer. Okay, so this was for a high-speed printer. I'll pass it around. It's made out of alumina, and they were making 250,000 of these a week for printers at the time. And they had an interesting problem, and the problem was that right along here in injection molding, along this line, it would crack. And we solved that problem. It was cool. The reason it cracked was what's called shear-induced segregation. Okay? And the reason was the temperature was too high and it reduced the viscosity and the segregation. These are great because the upper right 2 inches are tabular alumina, okay, which is an industrial alumina. There's 3 forms of alumina we typically see. These are examples out of the 203 class. The first lab, it's kind of entertaining. I do course evaluations, actually, every year. I read them every 3rd year. I don't know if this is the year I'm going to read them or I was supposed to read them last year. I can't remember. Okay? And the reason I read them every 3rd year is because it's human nature to focus on the negative. You know, so now I'll read this, it's like blah, 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 blah. So if I read it every 3rd year, I can find out if it's really a problem or not. Does that make sense? Okay? And so what happened is by reading course evaluations, never occurred to me if this was a problem. But what came back in the course evaluation is, why do we do ceramic processing? And you got to understand that I'm a little bit blown away by the question because course evaluations don't occur this week, although that's an idea. they occur at the end of the semester. You've been through the whole class in ceramic processing, and in the course evaluation, you asked me, why do we do ceramic processing? You can see why I might find that a bit baffling. So I introduced a lab, let you go in and play, make really poor samples, and then we evaluate them. This is why we do ceramic processing. That's where the images came from. Big honker pores in the upper left, clusters of particles, even the one in the middle. We have areas that densify before other areas, rather than this, which is pretty uniform in terms of microstructure, which is more or less our target. We'd like to do that. We'd like to also be able to control that porosity if there's a need to. Maybe I don't need it to be fully dense. We've been working with filtration materials, right? Need the porosity to make that work. How do we engineer that porosity to be exactly what we want, right? So that's another aspect of processing. So that's where the images came from. All right. So very briefly, when we talk about powders, when we talk about powder characterization, everything we do starts with powders. So the first thing that we're going to do is we're going to figure out how to characterize powders. That's not exactly true. First thing we're going to do in here is an introduction to mechanical properties. How many of you had, what's it called? What's that?
Microscopy?
No. Yes, fractography. Go.
Properties of materials. Thinking.
You deal with mechanical properties in there?
Mechanics of materials.
So you haven't dealt with it. Have you dealt with, what's it called? Thermal, electrical, and mechanical? ELMO or whatever it's called? That's optical in there somewhere. There's two classes. You haven't had those yet, right? Okay, good. So because of this idea of cracking and warping, I start with mechanical properties. Okay, so we're going to spend the next week or so dealing with mechanical properties. If you look at your homework set, the question is draw a schematic stress-strain relationship. Well, it seems to me that maybe I should teach you what that is before I ask you to draw. Okay, so we're going to do that over the next week or so. And the reason that we do that is that we have data that indicates that during the sintering process, the flaws don't go away. In other words, the flaw that you introduce in the process is the flaw you have at the end when the system is fully sintered. And the conventional wisdom says that in sintering, right, we eliminate those defects. That the pores are the defects that control the strain. And what we demonstrate is that that is not true. In fact, the strength that you measure, okay, at the end represents the flaws that you introduced in the beginning. That concept is really important because it drives home the idea that these materials, right, and the defects that you generate are formed in the process, and they're not eliminated in sintering. Okay, so that's why we do that. We start with mechanical properties, and then we go into powder characterization because everything we do starts with powders. And how do you measure the properties of the powders, and how does that impact the process? So we do that. Then we get into colloidal behavior, defect generation, etc. Failure on sintering or drying is usually a result of the process step. So in general, we get the plus side. Here's the plus side. Ceramic manufacturing processes are interesting in that they essentially identify a composition or a system that works within their process. That sounds a little strange. What they're doing is they work in the sweet spot. They work in an area where small variations in packing efficiency or mixing do not result in a significant difference in shrinkage. The consequence of that is that they can actually manufacture parts and put them in a box and send them out. Okay? It's in many respects a self-correcting idea. They come up with a composition that works in the process. Okay? And rather than the other way around, well, we're going to go make the perfect material and then hope we can make it. That's not the way it works. So you might set up a statistical experimental design with a dozen compositions, and you're going to home in on composition number D, or letter D, and that one works in the process. And that gives you the best results. The reason that you did that is because all those process steps influence that material, and that material is able to withstand those variations in process steps, and you can make that part. Okay? So there's a plus side. The formulas are often chosen not firsthand, they're chosen because they work. You come in and say, I really want it to be this. That's not what it is. You've got a process set up, you make changes to the body going through that process. Those changes, if they throw the behavior of the material off to where it doesn't work in the process, it doesn't work. But you will gravitate to compositions that work. Okay? Our opportunity is to understand why and how we can manipulate that for the current process. Okay? General outline, overview of working, cracking, strength of materials, parts of packaging, processing, etc. Okay? Listed in here someplace was powder characterization should probably be part of the packaging. All right, that's where we sit. So, ground rules, homeworks, I'm not going to grade them. I'll make that abundantly clear. If you want to meet with me, email Krishna, please. You're welcome to copy me, but she's really good about taking care of things on her own. Okay. If you have questions, you can post them to Canvas or bring them to class. And I will answer any question on the homework that you have. Fair enough? Okay. Have a great day. Welcome back. Enjoy your first week. Thank you.
You're timing that other part, that's making it
Perfect. Hi.